This conference will now be recorded.
Good
Hello,
afternoon, Abdul, Razak.
Sir, very good afternoon, sir. Thank you.
Am I audible?
Yeah, now audible.
Yeah, okay. Now first I will introduce. So later
Yes, sir.
it will be handed over to you. You can start. So
Yeah.
good afternoon to all the participants. I welcome all the participants for the 4th day of faculty development program on research trends in thermal engineering. So today, we are inviting the young and energetic researcher, one more researcher, where the today's speaker name is Dr. Abdul Razak Buradi. So presently he is working as assistant professor in the Department of Mechanical at NITTE Institute of Technology, so Bangalore. So coming to his educational profile, he just completed diploma in 2006 in automobile engineering from Government Polytechnic, Vijaypura. Then later he did Bachelor of Engineering in Mechanical from BLDA's Vachana Pitamaha Dr. PG Halkatti College of Engineering and Technology, Vijaypur. So further he pursued his MTech in Thermal Engineering from once again Dr. PG Halkatti College of Engineering and Technology, Vijaypur in the year 2013. Then it made him to incline towards the research, and as a result he took admission for the doctoral program at NITK Surathkal. In thermal, he did PhD in thermal engineering, specialization in computational fluid dynamics. So presently he is the assistant professor in the Department of Mechanical Engineering at NITTE Institute of Technology, NITTE Meenakshi Institute of Technology and Management, Bangalore. So beside this, so he has published so many national and international journals of around 7 in reputed journals, international journals. He has attended and presented the papers in international conferences of around 17, and the research interests of the today's speaker is heat transfer, CFD, that is computational fluid dynamics, biofluid dynamics, IC engines, and R&AC. Apart from this, he is also a life member of the Combustion Institute, and as well the life member of the Hong Kong Society of Mechanical Engineering. So he has attended the short-term training programs, workshops, faculty development programs of around 20, and during his teaching profession, he has handled the subjects like fluid mechanics, CAED, turbo machines, ATD, BTD, that is basic and applied thermodynamics. So with this introduction, so now he is expertise in computational fluid dynamics, and he is going to present the topic on cardiovascular fluid mechanics. It is a multidisciplinary research. So, and he is the only man I found when I was pursued. He is the only man where I found him in NITK Surathkal Department of Mechanical Engineering working on CFD, and he is the first person I saw him in the department to work on CFD under the expert, one more expert of his supervisor, Dr. Arun Mahalingam. Right, sir. With this introduction, now I request all the participants, if any queries you have come across, you please post it in a chat box so that at the end of the presentation our speaker can answer them. So if with this, now I will hand over to Dr. Abdul Razak Buradi to take up the presentation. Right. Thank you. Thank you.
Yes.
Yeah. Sir,
Thank you so much.
You please go ahead. Yeah.
Thank you so much for introducing me.
Go ahead. Yeah.
First, I am very thankful to the management of Buradi Institute of Technology and Management for giving me an opportunity to give a small lecture on a topic called as cardiovascular fluid mechanics, a multidisciplinary research. Presently, I am working in NITTE Meenakshi Institute of Technology as assistant professor in mechanical engineering department. Today, I want to give a a small presentation on this cardiovascular fluid mechanics, a multidisciplinary approach. Sir, I am audible, no, sir? Hello, sir. Sir, I am audible.
Yes, sir. Yes, sir. It's audible, sir. You can go ahead.
Thank you, sir.
Audible.
Okay, sir. So the main overview of my presentation is I'm going to explain in little bit more about introduction of fluid mechanics, introduction of human cardiovascular system, and terminology used in cardiovascular system, the blood composition and its viscosity, cardiovascular diseases and disorders, quantitative descriptors of arterial flows, and I also give small introduction about computational fluid dynamics. Based on this introduction, I will go to the two case studies. That is, case study one is the effect of stenosis severity on wall shear stress based hemodynamic descriptors using a multi-phase mixture of theory. And second case study is I'm going to explain is that impact of coronary tortuosity on artery hemodynamics. And by this we will go to conclusion and future scope of the study. So first we want to know generally this cardiovascular fluid mechanics is a multidisciplinary research. It mainly includes the mechanical engineers and biomedical engineers and also the cardiologists who are working on they are doctors. Okay. So as we are mechanical graduates, basically we studied this subject as one of our core subject in our graduate level, that is a fluid mechanics. Generally the fluid mechanics is divided in two parts. One is fluid, another one is mechanics. So out of this we first know that what is fluid. The question is arise in our mind, what is fluid? So we can say that a fluid is a substance with no strength, and also the fluid can deform when forces are applied. And the fluids may be, it include water or gases or maybe solid. If the fluid is a solid, it deforms a fixed amount or breaks completely when a stress is applied on it. And if a fluid is a water or gas, it deforms. We consider water a liquid fluid. It deforms continuously as long as any shear stress is applied on it. And what is mechanics? The very important concept. So mechanics nothing but the study of motion and the forces which cause the motion. Generally in mechanics there are three types. One is kinematics, it's also called as kinetics. So that gives the description of motion, that is displacement, velocity and acceleration. Another is statics. The statics nothing but the study of forces acting on the particles or bodies at rest. And the term dynamics is the study of forces acting on the particles and the bodies which are in motion. So in overall, we can say that fluid mechanics is the branch of physics that mainly concerned with the mechanics of fluids and the forces acting on them. And the fluid mechanics helps us to understand the behavior of fluid under various forces and at different atmospheric conditions, and also to select the proper fluid for various applications. Yes, we also know that it has applications in a wide range of disciplines, including mechanical, civil, chemical, geophysics, oceanography, meteorology, astrophysics, biology, and biomedical engineering. So we know in fluid mechanics, we also know that some stresses will arise when forces applied on them. That we know that stress nothing but force per unit area. There are two types of stresses acting on the fluid. That is, first one is shear stress. It is also called as tangential stress. So the shear stress is the force acting parallel to the surface per unit area of the surface. And second one is normal stress. That is a force acting perpendicular to the surface per unit area of the surface. And how do we study the fluid mechanics? Generally, we study the fluid mechanics by using the basic laws of physics that may consist of conservation of mass, like it is continuity equation, conservation of momentum, that is Newton's second law of motion, and conservation of energy. We can call it the energy equation, that is first law of thermodynamics. So we can study the fluid mechanics based on this law of physics and also the equation of state that mainly includes the fluid properties, various fluid properties, and constitutive laws. That is considering the relationship between the various stresses and the deformation of the material. And if particularly in blood flow dynamics, we can say that the cardiovascular fluid mechanics, we are basically concentrating on blood. Okay, blood is a fluid which is flowing in the blood vessels. Okay, so before going to that, the fluid flow, we know that fluid flow generally it involves the motion of a fluid that's subjected to unbalanced forces, and this motion continues as long as the unbalanced forces are applied on the fluid particle. And we studied in our graduate level, there are different types of fluid flows. Like there are 6 types of fluid flows. One is steady and unsteady flow, uniform and non-uniform flow, laminar and turbulent flows, compressible and incompressible flows, rotational and irrotational flows. Okay, and 1, 2, and 3 dimensional flows. But I don't want to explain all those things. But as for our cardiovascular fluid mechanics, I am more concentrating on the laminar and turbulent flows. Okay, this is very important for the cardiovascular fluid mechanics study. So the first thing is that we are considering here the blood vessels. We can call it a blood vessel, nothing but arteries, okay, or veins or capillaries. So we are considering in cardiovascular fluid mechanics as the pipes. Okay, if you want to go the principle to know the principles of fluid flow in the pipes, that first one is laminar. We are considering laminar and turbulent flow. As we all know that a laminar flow is the flow in which the fluid travels as a parallel layers and that do not mix as they move in the direction of the flow. And if the flow is turbulent, it means that the fluid does not travel in parallel layers, means there is a zigzag motion of the fluid will be there. And but in turbulent flow, the fluid moves in a haphazard manner with only the average motion of the fluid that being parallel to the axis of the pipe. And sometimes we may get the fluid is transitional flow. So that transitional flow is existing. If the flow is transitional, then both types of flows, that laminar and turbulent flow, may present. If you see this figure, the clear explanation of laminar and turbulent flows. So I have 2 figures here. One is that candle smoke is showing the 2 regimes, that is laminar flow and turbulent flow. So here, see, if you see the laminar flow, there is no any disturbance in the flow. Means flow will be in like streamlines. There is a very smooth flow is there and is highly ordered in motion. Okay, and if you see the other figures, that is the behavior of colored fluid. See, here we are injected a dye, that colored fluid in the pipe. Okay, if you see the laminar flow figure, that figure A, in which the dye is moving in very smooth and like streamlines and very highly ordered manner, whereas in B, for the turbulent flow, the flow is very disturbed flow. Okay, because disturbed flow means there is a lot of velocity fluctuations are there, and also it is highly disordered motion. And also in general, the most of the flows encountered in practice are turbulent. And if you come to the cardiovascular fluid mechanics, generally in blood flow through arteries, the flow is considered as a laminar flow. Sometimes because due to the deposit of cholesterol, we can say that lipids or plaques, the blood vessel becomes there is a deposit of, because of formation of plaques or lipids, the flow disturbance will happen. Then flow we can call as the term stenosis. Okay, so because of presence of stenosis in the blood vessels, the flow becomes turbulent. That I will explain in detail in coming slides. And also we know that some transient flow also is there. It is in transient flow, the flow fluctuates between the laminar and turbulent flows. And in 1883, the observer Reynolds, he performed a classic set of experiments that showed the flow characteristics that can be used for predicting the flow. Okay, we are using, that is the term is Reynolds number. Generally, we know the Reynolds number is the ratio of inertial forces in the flow to the viscous forces, and it can be calculated by using relation RE is rho Vd divided by mu, in which rho means it is density of the fluid in kg per meter cube, and V is the mean velocity of the fluid, and D is the diameter, pipe diameter, or we can say the vessel diameter or artery diameter, and mu is the dynamic viscosity of the fluid. Okay, and based on Reynolds number, we are classifying the flow, laminar flow and turbulent flow. If the Reynolds number is less than 2000, then the flow will be laminar flow. If the Reynolds number is more than 4000, then the flow is called as turbulent flow. And if the Reynolds number is in between 2000 and 4000, then the flow is called as transitional flow. Okay, but if you see the particular in blood flow dynamics, the Reynolds number will not go to the 2000 because Reynolds number very less here. So we are considering 200. If the Reynolds number 200 in the blood vessels, then it is laminar flow. If it crosses 400 Reynolds number, because the artery diameter is very small, like it is in mm or in microns, okay, or some aorta will be there, like it is aorta that is in 2 centimeter diameter. Okay, the blood vessels are very smallest diameter, so the Reynolds number also very less compared to pipes. Pipe is different, here blood vessel is different. Okay, and if you see the next, we are going to the human cardiovascular system. So the figure shows a heart, like we have human heart. So in which if you see the figure, the heart consists of various flows, like various pipes. We can say that generally the cardiovascular system, the term cardiovascular comes from the Greek word cardia. It means a heart, and Latin vasculum, that is vessel. Generally in human body, the heart is a complex muscular pump that maintains oxygenated blood circulation through the lungs and the rest of the body. And so in a cardiovascular circuit, the blood flows from the heart through the various blood vessels called as arteries, arterioles, capillaries, veins, and then come back to the heart. It's like it is a pump. The heart is act as a pump in which the blood is circulated continuously, like it is a closed system. Okay, and if you see the vascular nature of our body, so it is a heart, there are kidneys are there. So see, if you see the human body, it consists of number of blood vessels. If you arrange it in a straight line, then if you see the structure, the heart pumps the blood through an estimated, that is 1,20,000 kilometer of blood vessels. The human body consists of 1,20,000 kilometer of blood vessels, meaning pipes, with a total surface area of 800 to 1000 meters square. And generally the heart pumps more than about 14,000 liters of blood in a day. In each day, the heart pumps the blood of 14,000 liters. If you consider in a year, it takes 5 million liters of blood it pumped by heart in a year. And these blood vessels, they provide, means they act as a transport medium which supplies the nutrients, proteins, and oxygen to the various tissues and various parts of the body. Okay, and also the pressure in the blood vessel is varies from 5 mmHg to 120 mmHg with flow velocity is 0.03 centimeter per second to 40 centimeter per second. And generally in human cardiovascular system, there are two circuits. Then we can say that systemic circuit and pulmonary circuit. See, in our presentation, I'm concentrating more on the human cardiovascular system, because based on that, I want to explain you what is the application of fluid mechanics is there in the human fluid mechanics, that is cardiovascular fluid mechanics, and also what are the applications and how it helps to the tackle the various cardiovascular diseases. Okay. See, there are two circuits in the cardiovascular system. One is systemic circuit, another one is pulmonary circuit. So this systemic circuit supplies the oxygenated blood, or it transmits the oxygenated blood flows from the heart into various capillary beds where it gives up O2 oxygen and takes up the carbon dioxide CO2 and then flows back to the heart. It's like circuit, systemic circuit. And another one is pulmonary circuit. So this pulmonary circuit, it takes deoxygenated, it supplies the deoxygenated blood from the heart through a pair of lungs, then back to the heart. Okay. And this is a clear explanation of these two circuits, pulmonary circuit and systemic circuit. The figure shows the systemic circulation of the heart. Here you can see in this, there is a color of the red one is there, and another blue one is there. So here the red indicates the blood vessels carrying the oxygenated blood, and the blue indicates the blood vessels carrying the holding the deoxygenated fluid, like less oxygenated blood in blue color. And generally this systemic circuit is the portion of the circulatory system that carries oxygenated blood away from the heart and delivers it to the most of our organs and tissues, and same thing returns back to the your heart again. So that is circuit, closed circuit. And if you see the pulmonary circuit, here also same thing. The red indicates the blood vessels carrying the oxygenated blood, and blue indicates the blood vessels carrying the deoxygenated blood. And if you want to explain the pulmonary circuit, the pulmonary circulation is the portion of the cardiovascular circular system which carries deoxygenated blood away from the right ventricle. So there are right ventricle, left ventricle. These all are biomedical terms. A little bit difficult to understand those terms. So here the pulmonary circulatory system, the portion of deoxygenated blood is this in this portion, some circulatory system which carries the deoxygenated blood away from the right ventricle to the lungs and returns oxygen blood to the left atrium and ventricle of the heart. So if you see this one, blood vessels of the human cardiovascular system. See here we can see clearly the various vessels or arteries are present in the human body. There are a lot of arteries. So generally, basically, carotid artery, coronary arteries, and also iliac arteries, femoral arteries. Different types of arteries are there. Again, there are different types of coronary arteries, left coronary arteries, right coronary arteries, like that. Okay. So if you see this one, the importance of fluid mechanics is very much essential for the cardiologist. Okay. So how the blood flows in the blood vessels, where if any disturbance arises in the blood vessels, how the blood behaves inside the blood vessels. The very interested things to understand to tackle the cardiovascular diseases. And if you see this whole blood vessels, we are classifying this with different types of blood vessels like arteries, arterioles, capillaries, venules, veins, and each blood vessels has its function. If you see the arteries carries blood from ventricles to the arterioles, and arterioles function is to control blood distribution to the capillaries, and capillaries exchange the various substances nothing but your nutrients, proteins. Okay. And venules, it collect blood from the capillaries, and veins, because veins is very important term here. The veins deliver the blood back to the heart, and the figure shows a typical artery and a typical vein. Okay, see here, one part is artery, another one is vein, and here generally the arteries are blood vessels that are responsible for carrying oxygen-rich blood away from the heart to the body, whereas the veins are blood vessels that carry deoxygenated blood to the heart for reoxygenation. Okay, so these are different structure. And if you see the blood vessels and its structure, here I have shown the lumen. Generally, the blood vessel consists of 3 layers. We can call the first one the lumen. Lumen means the inner layer. If you see the figure here, the inside one is the lumen, where the blood flows. Again, the blood vessels consist of 3 layers. One is tunica, intima, media, and tunica externa. There are 3 layers. Okay, and generally the blood vessels are varying the dimensions. If you see here the diameter of the various blood vessels, the artery has mean diameter 4 mm, and mean wall thickness is 1 mm. So very small thickness and small diameter. Okay. If you see the arterioles, that the diameter of the arteriole is in micron. So we can expect that it is in human blood vessels, the both microfluidics also applicable. Both microfluidics, and like we can consider the blood vessel as mini channels or micro channels. If you consider artery is a mini channel, so we can study the behavior of blood or fluid in the mini channels like arteries or in macro channels. Okay. So also the physics of macro channels also applicable to biofluid mechanics. So it's like one of the research interest. So if any persons are interested to work on this biofluid mechanics, they can consider these macro channels. Okay. And also the capillaries. See, if you see the dimensions here, we can say that the blood vessels diameter varies from 8 micron to 5 mm. Okay, if aorta is the biggest blood vessel in the human body that has 2 centimeter, maximum 2 centimeter of aorta. And next, structure of human blood vessels. Again, I am explaining here same thing, like different parts, how the blood vessels consist. See, if you see the figure of arteries, it has 3 layers, I told, right? One is tunica, intima, media, and adventitia. And also this lumen. If you see this endothelium, see this lumen where the blood flows. So here, the surrounding of the lumen is, it consists of endothelial cells, we can call. It is a very smooth, flexible a layer of the tissue layers. Then where generally this is your deposition of blood, what you call cholesterol or LDL, HDL, that will deposit here only because of the flow disturbance arising in the blood vessels. So this is the outer layer. If you see the function of this, the arteries carry oxygenated blood away from the heart, and these arteries are having more thicker than the veins. Again, generally these arteries are in a circular cross section. If you see the arterioles, and this is the same, it consists of various layers. And arteriole is a very small artery that leads to a capillary, and the arterioles have the same 3 layers as arteries. Okay. And if you see the capillaries, it is a structure of capillaries and structure of veins. So if you see the function of capillaries, a capillary is a microscopic channel, we can call it a micro channel, that supplies blood to the tissues, because human body consists of various tissues. The capillary is the medium to supply the blood to the tissues. And also the capillary exchanges the gases and other substances between the blood and surrounding cells. And the diameter of a capillary is varying from 5 to 10 microns. And if you see the veins are the blood vessels that carry blood towards the heart, and most of the veins carry the deoxygenated blood only from the tissues to the heart back. Okay? And the various terminologies, we are using various terminologies in the cardio system, because you may come across, if you visit a doctor like cardiologist, like they may check your blood pressure, we can call BP, okay, maybe high BP or low BP. Okay, let's have different blood terminology there. And also, if you see the in ECG, like one cardiac cycle will be there. The variation of BP, blood pressure varies, like systolic pressure, diastolic pressure. Some terminology are first cycle, like the cardiac cycle. It is duration there. If 0.6 to 1 second, the 1 cardiac cycle, we can say that. Like the cardiac cycle is from the ending of one heartbeat to the beginning of the cardiac cycle refers to generally the cardiac cycle is associated with blood flow through the heart. There is systolic term is there and diastolic. The systole means it contraction of heart muscle, and diastole is relaxation of heart muscle. And the other term is blood flow. The volume of blood flowing through a vessel or organ in a given period is represented by a milliliter per minute. The overall blood flow in an adult, like in adult human, is about 5,000 milliliter per minute. Per minute, that much milliliter is flowing through the blood vessels. And like venous return, it is some terminology used in the cardiovascular system. That venous return is the amount of blood flowing into the right atrium each minute. Okay, and it's approximately 5 liters per minute. And also we are using the term called as stroke volume. So it is the amount of blood ejected from a ventricle with each heartbeat. So it is usually 60 to 10 milliliter. And cardiac output we are using. So this cardiac output and peripheral resistance it is used to calculate the blood pressure. Okay, it is the amount of blood pumped into the aorta each minute by the heart. Like this, generally the cardiac output is for the normal person is 5 liters per minute, and peripheral resistance, it is the resistance to the flow of blood determined by the vessel diameter. And the term blood pressure is very important to understand the various cardiovascular diseases. So the blood pressure nothing but it is the force, or you can say the pressure of blood exerted on the walls of the arteries or blood vessels. Generally, this blood pressure is calculated by the using of cardiac output and peripheral resistance. And the normal blood pressure in a normal person adult is 120/80. So 120/80 means here 120 is systolic pressure and 80 is diastolic pressure. Means blood pressure should not vary. It should not go more than 120 and it should not be less than 80. That is normal BP. And if high BP comes, that high blood pressure is, it should not be more than 140 or more than, not less than 9, means not more than 90. That high BP we can call the systolic and diastolic pressure. And if you see the systolic pressure, the systolic is the maximum pressure during systole. It is 100 to 140 mmHg range. And for a normal person, is the systolic pressure should be 120 mmHg. And for diastolic pressure, it should be minimum 80 mmHg. So this is the figure shows the variation of blood pressure for different blood vessels like arteries, capillaries, and veins. If you see here in the plot blood pressure versus various arteries, the blood pressure is the pressure exerted by blood on the walls of the blood vessels, and the blood pressure is highest in arteries. If you see these arteries, the blood pressure is very high, that is varying from 80 to 120. So that 80 is diastolic pressure and 120 is systolic pressure. Generally, if you go to the hospital, the doctor first will check your BP, blood pressure. If the blood pressure varies from 120, if 120 more than 120, then they can say that he has some symptoms of some cardiovascular diseases, like high BP, like we can say that hypertension, okay, like diabetes. They will link so these blood pressure with different diseases. And also the rate of blood flow in blood vessels is mainly depends on the difference in blood pressure between 2 points and resistance to the flow. And now I am going to the blood composition and its viscosity. So what we studied now, it is like what is fluid mechanics is there and what is the cardiovascular system. Okay, now we come to know that the fluid mechanics is very much essential, or knowledge of fluid mechanics is very much essential for the cardiologists, like doctors. The doctors are not free, so they are not able to study the fluid mechanics. So they need the help of mechanical engineers or also biomedical engineers. So they're working on these various, they're studying the various blood behavior in the blood vessels. If you see here, generally blood is we can say that blood is a Newtonian fluid, and also another term of mechanical comes here, that Newtonian fluid and non-Newtonian fluid. Okay, so Newtonian fluid, we know that if the fluid satisfy the Newton's law of viscosity, then we say that Newtonian fluid. If they not satisfy the Newton's law of viscosity, then it is a non-Newtonian fluid. Generally, in human blood, we can consider it as a multi-phase fluid. Why multi-phase? Because the blood consists of various blood particles like red blood cells, white blood cells, platelets, or some cholesterol. We can say LDL, HDL, like that. Okay, different terms are there. If you see the figure here, generally in blood, a plasma is more percentage is there. Plasma, nothing but it is like water. Like up to, if you 100% of the blood, 55% of blood is consists of plasma, and 45% of blood is red blood cells, and 1% of blood consists of your white blood cells, platelets, and other lipoproteins. Okay, and also the blood viscosity is an important term. And this blood viscosity, based on blood viscosity, we are classifying the Newtonian and non-Newtonian fluid. If you see here, the blood viscosity is very much depends on shear rate. So generally in low shear rate, the blood is act as a non-Newtonian fluid, and as the shear rate increases to up to 1000, then the blood acts as a Newtonian fluid, like plasma. So if you see the another figure, so see in low shear rate, the red blood cells started aggregating. It forms a relaxed nature. Okay, and as the blood shear rate increases, the blood becomes Newtonian fluid, means that relaxed nature will be breakout. So here I explained the effect of viscosity on resistance and of blood flow. Generally, the increasing viscosity increases the resistance and thus decreases the rate of blood flow. and the viscosity of blood increases as the hematocrit increases. Hematocrit nothing but here blood volume fraction. Okay, and also the hematocrit is the percentage of red blood cells presence in the blood. And the important thing is that what are the challenges in fluid mechanics of blood flow? Generally, the blood in the blood vessels is very complex fluid, and also the important factor is the rheology of blood, means whether we consider a non-Newtonian fluid or Newtonian fluid. And generally, the blood vessels are very flexible; they are not rigid. Okay, and also the pressure wave travels along the arteries, like because in arteries the blood pressure is not same, like it is varying based on as the diameter of the arteries changes. And also the blood vessels frequently encountered by bifurcations. If you see the blood vessels, they are not a straight pipe, like there may be some curves or some tortuosity will be there, or some bifurcations will be there. Okay, and there are very small veins also there. These are very important challenges for biomedical engineers or mechanical engineers. And the question arises, why we study the fluid mechanics of blood flow? We have to study the fluid mechanics of blood flow because the different people develop different vascular diseases in the same places. Okay, and so the only thing unique about all these is the vessels is their shape and the flow inside them. The flow is same, so that we can kind of study the fluid mechanics. And also the studying hemodynamics, like blood flow dynamics, helps us to understand the why vascular disease develops and how to prevent or treat it, and what can we learn from studying the cardiovascular flow. So to studying the cardiovascular fluid mechanics it helps us to the early diagnosis of cardiovascular problems. These are all application to doctors. Okay, they come to know that early diagnosis, what they can do, where will disease develop, and if the disease develop, is whether the disease is likely to worsen or not. Everything they will understand by this our cardiovascular fluid mechanics. And also drug delivery planning. So it's also helpful how we cardiologists understand how can we get the medication to a particular place, a particular disease, and where does medication end up if we inject it randomly. Like that, they will all understand by our cardiovascular fluid mechanics results. And also they can also know the designing of smart medical devices like stents, LVD, infusion pumps, etc. And now comes to the cardiovascular diseases. So we studied cardiovascular fluid mechanics, cardiovascular system. Now we are approaching the cardiovascular diseases. They're very important. The diseases, okay. Generally, there are different types of diseases are there. So here we are concentrating more on cardiovascular. Like main thing, first one is that atherosclerosis, or they also called arteriosclerosis. See, the atherosclerosis is a disease in which the hardening or thickening of the artery blood vessel takes place due to the buildup of lipids like cholesterol in the artery wall that narrows the lumen that may rupture and trigger the heart attack. Okay, and also hypertension. The hypertension nothing but the high BP. It is a silent killer. Generally, the chronic blood pressure above 140 to 90, and high blood pressure and atherosclerosis increase the risk of heart attack and stroke. These cardiovascular disorders are the leading cause of death in both the developed and developed countries. Okay. And we see the first one, atherosclerosis or arteriosclerosis. The atherosclerosis is a chronic degenerative disease and common health problem in which the thickening and hardening of the artery wall takes place. And this atherosclerosis disease, the disease of the arteries, characterized by thickening or loss of elasticity or and calcification of artery walls, and this resulting in decreased blood flow, blood supply, particular to this cerebrum and lower extremes. And often this atherosclerosis it develops with aging. As age comes, as age goes on increasing, this disease will arise or due to hypertension or due to diabetes. If you see the atherosclerosis, okay, generally the atherosclerosis is a focal disease. Generally it takes place in bends, where the bends of the blood vessels are bends or branches or bifurcations. So this disease will present, and this disease mainly occurs due to the disturbed blood flow. If you see here, first one is blood flow is straight without any disturbance, and second figure has the blood flow varies or due to the deposition of plaques or cholesterol in the blood vessels that form the stenosis. That stenosis makes blood flow will be difficult. So there is a flow recirculation starts, and due to that flow recirculation, continuous flow recirculation or flow suppression, there is a endothelial cell dysfunction will be happen. Okay, here you can see the figure here, the deposition of plaque or cholesterol inside the blood vessels that disturbs the blood flow, or if this plaque exceeds the limit 95% or 80%, then there may chances of rupture of plaque rupture. So that we can say that a heart attack or stroke will happen. And this is a figure of how the front view of heart showing the cross section of various arteries. Like this is a normal artery without any damage. Okay, this is diseased or narrowed arteries with some percentage of plaque deposition. And third one, diseased or blocked arteries, fully blocked arteries. The progression of atherosclerosis, how the disease will progress. Generally, we studied that the atherosclerosis or cardiovascular disease happen only in the bifurcations or bends, okay, or where the branches will be there. So due to the presence of plaque or cholesterol in the blood vessels, that restrict the blood flow. Okay, then this deposition of plaque or cholesterol act as a blockage. We can call it the stenosis. And these are the various evidences suggest that the initiation and progression of atherosclerosis disease is mainly influenced by the disturbed flow. Okay. Now it comes to coronary heart disease. Generally, the more than 7 million Americans are affected due to the coronary artery disease. Generally, this coronary artery disease or coronary heart disease is mainly caused by narrowing of coronary arteries. Okay. Generally, due to this disease, every year more than 5 lakh are die because of this cardiovascular diseases, and more than 2,600 Americans die each day because of coronary artery disease. That means one death per 33 seconds. And this is how the coronary artery disease will happen. Generally, this coronary artery disease is nothing but the deposition of plaque or cholesterol happening more in the coronary arteries. Like these coronary arteries are surrounding the heart. There are two types of arteries, one is right coronary arteries or left coronary arteries. Generally, the research shows that the left coronary arteries is the main arteries where generally the block will happen. So if a patient visits the cardiologist, first they will check your, they will do angiography or angioplasty, where they will inject your one catheter, and that catheter they passes in the coronary arteries only. They will check first in the coronary arteries disease. Okay. The main risk factor for this coronary arteries, or you consider any cardiovascular disease, is high blood pressure, that we call hypertension, high blood cholesterol, smoking, obesity, physical inactivity, diabetes, and stress. These all are the risk factors. These risk factors can be controllable. We can control these risk factors, and some risk factors we can't controllable. That is gender. Generally, it happens in more in men's, and heredity, like it is hierarchical. Heredity also one can't control factor for these cardiovascular diseases, and age also. As age goes on increasing, this disease may arise. And the major risk factors, there are these are the three big factors which affect more on the, or that lead to the cardiovascular diseases. First, hypertension, high cholesterol, and cigarette smoking. And also due to the lack of exercise also lead to the cardiovascular diseases. So that the exercise are very most essential. And this is the variation of graphs for different risk factors, and is the percent of risk. If you see here, the inactivities leads to the more risk of cardiovascular diseases. And hypertension, like high BP, generally this hypertension is commonly called as high blood pressure. That systolic and diastolic measurements, normal systolic pressure will be 110 to 130 should be there. If it crosses 130, then you can say that high BP. And if in the normal diastolic pressure will be 70 to 90. If it comes less than 70, then we can say that it is a low BP. And symptoms of coronary artery disease. Generally, the main symptoms of coronary disease are chest pain, we can call it angina, and shortness of breath, heaviness or tightness, pain, burning, pressure or squeezing behind the breastbone or in the arms or neck or jaws. So if you have get any pains in the arms or necks, that is one of the symptoms of coronary artery disease. And also pain may vary for different persons, and perhaps no pain also the disease will arise. And where the cause and consequence of coronary artery disease, lack of oxygen due to ischemia, the lack of blood supply, and narrowing of coronary arteries, heart response with angina, finally heart attack, like in myocardial infarction. This heart attack generally happen usually due to thrombus, like clotting happen in the blood vessels, clotting, and embolus or clot that has moved from another side to the large and smaller vessel. And for our cardiac fluid mechanics, we are considering the cardiac quantitative descriptors. So we can say that the various hemodynamic descriptors of arterial flows lead to the cardiovascular diseases. If you see here, the blood flow data contain valuable information for diagnosis, prognosis, and risk assessment of cardiovascular diseases. And the hemodynamics, like blood flow dynamics descriptors, are used to visualize a disturbed flow, to perform quantitative comparisons and measure hemodynamic performances of surgical interventions, device optimization, or follow-up studies. The effective flow visualization of facilities, a better understanding of the physical phenomena, and also open new venues of scientific investigation. The various hemodynamic factors or forces on blood flow is the main role of hemodynamic forces acting on the vessel wall is the fundamental in maintaining the normal functioning of the circulatory system. So it means in the blood vessels, the wall stress should be there, that should be present. So that only stress only continuing the normal functioning of the heart or blood vessels. That and also the wall shear stress should not vary more. There is some threshold values are there that I will explain in coming slides. If you see the wall shear stress, this is the main hemodynamic parameters that producing a tangential force on the vascular endothelial cell or surface near the wall. So we can say wall shear stress and stretch are the most important hemodynamic forces involved in the blood vessels. So it is calculated by using this relation wall shear stress. To calculate this wall shear stress, we depend on CFD. If you see the here wall shear stress and endothelial cells, if you see here, I have two figures. One is steady flow. So when the flow is laminar, there is no any disturbance in the endothelial cells. These are the endothelial cells. There is no any disturbance when the flow is steady. When the flow is disturbed flow, like flow is oscillated, like means there is a flow recirculation happen in the blood vessels due to flow recirculation, or due to backflow, or due to flow suppression. There is a disturbance in the endothelial cells. Okay. Due to the disturbance in endothelial cells, the particles may get more time to get settled down, like your cholesterol or white blood cells or platelets get settled down here. Because of settling down of this cholesterol or white blood cells, that lead to the formation of your lipids. We can say that for plaques. Okay. And this is the how the disturbance will be there. If you see here, because of the presence of stenosis, we can call the flow is laminar without any disturbance, and because of turbulent flow, due to disturbed flow, what happens? The flow recirculation happen. Due to flow recirculation, the particles may get time to get settled down, and generally this flow recirculation happen in the downstream of the stenosis. If you consider this as a stenosis, the upstream is flow will be laminar, that low wall shear stress, and at the place of stenosis, there is a high wall shear stress there. As the flow comes in the downside, there is a flow recirculation happen. Due to flow recirculation, there may chances of deposition of white blood cells or platelets. Okay, that may lead to the plaque increasing, or lipids should be increased. And these are to measure this wall shear stress, we are depending on CFD, the computational fluid dynamics. So these are the different steps how do we get the images for CFD analysis. That is step one is the experimental we can do, or we can get the images from the cardiovascular images like MRI scan image or CT scan image or ultrasound images. Okay, intravascular ultrasound images. By that images we can create these models and their profiles. Again, we can make in CATI as a surface model, and we do the volume mesh in any meshing softwares like ICM CFD or ANSYS Workbench or Gambit software. We can do meshing and do the analysis. So here CFD term comes as we know that computational fluid dynamics. Nowadays it is a emerging field in the mechanical CFD. The CFD uses the various computational methods for solving fluid engineering systems, including mathematical and physics and numerical methods, solvers, finite differences, and grid generations. The main objective of the CFD in cardiovascular fluid mechanics is to model the continuous fluids with partial differential equations and discretize the partial differential equations into an algebra problem and solve it and validate it to achieve the simulation based results. And the fluid dynamic approach uses the geometry and mechanical properties of the vasculature and the principles of conservation of mass, a continued equation and momentum equation to obtain the blood flow pressure relations. And also the main goal of CFD in blood flow is the main goal of fluid mechanics in cardiovascular fluid mechanics is to solve the Navier-Stokes equations which govern the most of blood flows. Okay, generally, these are equations for blood flow. So here mass conservation equation is there, momentum conservation equation is there. So that mass into F equal to m into E, like second law of motion. Then no need to go to in detail of these equations. Now how the CFD process will be there. Like to analysis the cardiovascular, like if you want to analyze the blood flow, how the blood flow is there inside the blood vessels, how the blood behavior is there, the systemic process is there. So the CFD process consists of first geometric preparation and physics involved, and meshing will be there, and a solution will be in the ANSYS Fluent or ANSYS CFX, anything you can use, any softwares, and also you get generate the reports in the form of XY plot or verification, and you have to do validation. Once everything is done, we have to do post-processing. Like we get the results of velocity variation or pressure variation in the form of contours or vectors or streamlines in detail process of CFD. And we have different softwares for this analysis of cardiovascular fluid mechanics. Like CFD software is there, like Fluent, Flow Lab, Star CS or Star CD or CFX, and also grid generation softwares are available. Grid generation, Grid Pro, and also we can use the visualization factor like CFD post, tech plot, or field view. Okay. Now I'm going to the case studies. So what have we studied in fluid mechanics, cardio systems, and how the effect of this on wall shear stress. Now case study one. So here it is my study only. So what we did here, our main case study one is the effect of stenosis severity on wall shear stress based hemodynamic descriptors using multi-phase mixture theory. So the main objective of our case study one is to investigate the effect of stenosis severity on the pulsatile coronary hemodynamics. Okay, and here in this study we use blood as a multi-phase fluid, and by using mixture theory we analyze the blood behavior in the blood vessels, and also we studied the various blood flow hemodynamic descriptors. So we can call it as wall shear stress hemodynamic descriptors like wall shear stress, time average wall shear stress, the wall shear gradients, because these all descriptors have more influence on the cardiovascular diseases, like some threshold value that I will explain. And so the oscillatory shear index is also one of the important hemodynamic descriptors. Okay, that gives the variation of flow, like that flow is negative, like flow reversal it shows, and relative residence time. It is also one of the hemodynamic descriptors that pinpoints the regions of oscillatory, where oscillatory stress is there or where low wall shear stress is. And generally, the study shows that wherever low wall shear stress is available, there may chances of more deposition of your lipids or cholesterols. Okay, and also another term is ECAP. You can say the endothelial cell activation potential. It is also one of the hemodynamic parameters which used to study the blood flow dynamics. So these all formulas are there. These parameters we can calculate in the CFD. Okay, and some clinical threshold values are there. So the study shows that if the wall shear stress, if less than 1.5 Pascal, that leads to the intimal hyperplasia. That means thickening of the wall. If the wall shear stress regions less than 0.5 Pascal are more prone to the atherosclerosis, means wherever wall shear less than 0.5 Pascal, it leads to the atherosclerosis prone region. So generally, the cardiologists or cardiovascular surgeons, they are mainly concentrating on this parameter threshold values. Okay, based on this, our studies, our fluid mechanics studies, they can understand how where the disease will develop, how the disease develop, and which medication we have to provide. Like that, they will study. These are different threshold values. So, and these are all threshold values. And here, what we did in our study, in case study, we studied the idealized model. Means not rigid study we did. Means we some what we can say that it is limitations are there in this, because to get the blood vessel exact image of the blood vessel very difficult, because it is because of complex nature of blood vessels. So here we created a straight idealized model with varying the stenosis, like a degree of stenosis means deposition of plaque. Okay, here this is our model. So here is a inlet and outlet. Okay, and stenosis. We are our studies concentrating on the stenosis zone, and we modeled 4 models with different degree of stenosis. Like first one is 30% stenosis, 50% stenosis, 70% and 85%. So this stenosis indicates that if it is 30% stenosis, means 30% will be blockage will be there surrounding, and 50% means 50% blockage will be there, 70% means 70% blockage, and 85% degree of stenosis, 85% blockage will be there. So when this percentage of has blockage varies means deposition of plaque varies, how the blood behavior there inside the blood vessels, that we studied in this study. And also we did validations with experimental study. Okay, and here we selected the material properties like density of blood and density of red blood cells. So here we consider it a multi-phase. So we are considering here red blood cells. Okay, and also we did meshing, and also we did grid independent study also. Okay, meshing also we did meshing in ICM CFD, and this is the boundary condition we use, like the pulsatile. Generally, the blood in the blood vessel is pulsatile nature, not it is straight flow. Okay, because blood vessel velocity varying with the as the time process. Like it is one cardiac cycle we have selected that ranging from 0.1 to 0.75 second. And here in this study, we use the blood density of 1025 kg per meter cube, and red blood cell densities, RBC density 1100 kg per meter cube. And also we consider the red blood cells are spherical with 8 micron diameter, and there is no zero slip velocity at the wall. And these are the result discussions. So if you see the velocity distributions in the various stenosis, if you see here for 30% stenosis, so if you see this upstream and downstream, okay, this upstream section, there is no any disturbance in the flow, and because of presence of stenosis, there may flow disturbance will arise in the downstream of the stenosis. If you see the flow recirculation in the downstream region, so this same region will be increasing as the stenosis increases, like 50% stenosis and is 70% stenosis, 80% stenosis. As the stenosis increase, the flow disturbance is more in the downstream region, and because of this flow disturbances, that leads to the low wall shear stress or high wall shear stress. And again, we can conclude that in low wall shear stress, the deposition of disease may progress. Okay, and this is distribution of wall shear stress, and we can clearly say that in this, as the stenosis percent increases, the wall shear stress will increases exponentially by this table. Also similarly, time average wall shear variations, and also we can see here as the degree of stenosis increases, it affect on time average wall shear stress. Similarly, affect on wall shear gradient also the stenosis, and also oscillated shear index also increases as the degree of stenosis increases. So because it all they based on threshold values. In second case study is impact of coronary tortuosity on artery hemodynamics. So in this study, we investigated the impact of various tortuosity morphological indices on the artery hemodynamics. So generally, the figure shows this. Generally, the blood vessels are not straight or not a similar cross section because of presence of variation of blood pressure, everything. There may chances of tortuosity presence in the blood vessels. So that also we analyze here. So this we created this model, and here we vary the various bend angles, okay, bend section angles, and curvature ratio, angle of bend, and distance between two bends that we studied. And also we did grid independent study and meshing we done in ICM CFD. Okay, and results discussions in this. Here are the same discussions we did what we did earlier in case 1. So here you can see that velocity variation and wall shear variation. So clearly it shows wherever the low wall shear stress there is a low velocity there is a low wall shear stress, and similarly wherever low wall shear stress there is a low high RRT is there and high E cap is there. Means wherever low velocity is there only the deposition of cholesterol or lipids will increases. Okay, the studies are all asymmetrical. We did for different studies for 90%, 90 degree bend, 120 degree bend, and all I'm showing here one result only. We did for 4 angle of degree bends, like 90 degree, 120 degree, 150 degree, and 180 degrees. That results are plotted in the table. 90 degree angle of bend and angle of bend 120 degree, 150 degree, 180 degree, and also for varying distance between bed BBP 0.36 mm. Okay. And for the different curvature radius also we carried. And from this conclusion on both case 1 and case 2, we can say that our study what we did for multiphase fluid dynamics, it is for as our best of our knowledge, it is addressed for the first time, that multiphase blood flow study. Generally, because the literature in literature the blood is considered as a single phase fluid. Generally, the blood is not single phase because it consists of some white blood cells or red blood cells, etc. Based on that, it becomes multiphase, and we can say that in conclusion, we observed it is observed from our study is that the multiphase mixture model results were in good agreement with the experimental results compared to single phase model. Also, if the stenosis severity increases more than 50%, the wall stress is very high in stenosis region, that is throat, and the formation of recirculation zone is higher in post-stenosis zone region, like in downstream regions. And also, it can be concluded that the wall shear stress and wall shear stress based hemodynamic descriptors were significantly affected by the presence of stenosis and the increase in degree of stenosis. And also, our findings suggest that all the tortuosity morphological indices like curvature radius, distance between bends, angle of bends have significant influence on the distribution of various HDs, hemodynamic descriptors, and artery hemodynamics. And also, the sites of high OSI, low TAWSS are witnessed at the inner arterial wall downstream region of the bends in all the tortuous artery models. Okay. And however, the potential zones were found to increase as the angle of bend is increased. And for the scope of future work, this multiphase mixture theory blood flow model with components of blood in addition to red blood cells, we can also study with considering the white blood cells, because we did only consider red blood cells. If anyone interested in this research, they can consider the white blood cells or lipoproteins, HDL, LDL, or platelets they can consider. And here in our study, we consider the ideal models. For further research, they can go through the patient-specific models like patient images. They can get the patient images from the cardiologist from MRI scan or CT scan or ultrasound scan. They can get images and they model the blood vessels. And also, one of our limitation in this study is that we not consider any fluid structure interaction. That is also one interesting factor they can do for future study, fluid structure interaction, everything. Okay. And these are the references. Okay. And thank you. If you have any queries, please ask me, or you can text me, I will answer in the chat box. Sir, thank you. Yeah, taken time. Sir?
Sir, kindly answer the question, sir, that is put in the comment box.
Yeah, I will go through it. Checking.
Sir, a person named Manikandan Sakitwel, can you
Yes.
suggest a good software tool for solving multi-phase flow?
Sir, a good tool is ANSI Fluent is very good tool for that. ANSI Fluent. So maybe that if they are interested in multi-phase flow, maybe they are depending on that Euler-Lagrangian method, or there are different types of multi-phase tools are there. They can use ANSI Fluent is good, sir, for that to analyze the multi-phase flow dynamics. So I can suggest them is ANSYS Fluent you can use, or you can use a CFX also. But compared to CFX, Fluent is very flexible and user-friendly software. So I suggest that one for them. Any questions, sir?
Sir, 1 second.
Yes, sir.
Sir, no other questions, sir.
Okay, sir. Okay.
Okay.
So they can do, sir. This is one of the good in research topic nowadays.
Yes. Yes, sir.
Unlike
Yes, sir.
or anything, a lot of things are there. If they really want to do research on this cardiovascular mechanics, I suggest them better you have to approach any cardiologist or any doctors. They can give work like what they are facing in their medical field. Like if they're not understanding this is happen, how that we can do as a research work. Thank you, sir.
Okay. So just a minute, sir.
Yes, sir.
I'll hand over to Raghavendra Joshi, sir. Just
Yes,
a minute.
Dr. Abdul, this is Joshi.
Yes, sir. Thank you, sir. Tell me, sir.
Thank you,
sir.
sir. Nice presentation and nice slides preparation. and it was very informative.
Thank you,
Okay.
sir.
And also it is as I posted already 1 or 2 messages regarding this. It is a latest research topic where the people who are yet to register for PhD program can attempt on this area. Those who are belonging to thermal engineering specialization people.
Yes, sir.
So
Sir.
overall, very nice presentation, and I thank once again for having accepted our invitation and delivered a talk on multidisciplinary research pertaining to the computational fluid dynamics. Okay, Dr. Abdul, Razak, Buradi, I am very much thankful personally also. I am going to thank once again. Thank you, thank you, thank you.
Thank you, sir. Thank you for all the organization.
Thank you, thank you. That is what I said. So I am very much proud that you have been carried out the research in a multidisciplinary area, and where you have given a very informative delivery today to all the participants who are yet to register for the PhD program, those being associated to thermal engineering background. Okay.
Yes.
With this, now I thank the speaker once again, and I thank all the participants. I am going to conclude and leave the meeting. Okay, thank you. And Dr. Abdul, I request you, can you share your PPTs to my email ID so that if anybody would like to refer, they can refer, and I will also share your email ID so that they can approach you. So in turn, you can help them in excelling their research.
Yes, sir. Yes, sir. I can.
Right.
I can
You
open
your PPT, and at the end of the program, we too, the organizers, will share the presentation videos of all the speakers. Okay.
Yes, yes, sir. Yes, sir.
Oh, thank you, thank you, thank you, thank you
Text
once
in
again.
chat box my mail ID and phone number if anyone can use.
Yeah, yeah, definitely, I will share to all the participants. Okay.
Yes, 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 sir.
Thank you, Abdul. Thank you.
Thank you, sir. Thank you so much, and I'm very thankful to Department of Mechanical Engineering, BITM, for giving us this opportunity for presentations. Thank you, sir.
Thank you once again. Thank you.
Thank you, sir.